Hi, I'm Ben-Yaakov. This presentation is entitled Bipolar Gate Drive of Power Transistors. Now we are usually driving power MOSFET by unipolar pulses. Here I'm showing a driver, that's a gate resistor, and here's a gate of, say, a power MOSFET. And normally these will be positive going pulses because it's a enhancement mode MOSFET. And the range of the pulse is between, say, 0 and, say, 15 volt. This will be very typical. However, there is another way of driving gates of power switches, and this will be in a bipolar way, that is having a pulse which is going to positive, and then the 0 is not 0 but rather a negative value. Okay, so it goes to positive then negative. Of course, you have to make sure that you are not exceeding the maximum permissible voltage of the gate. Usually it will be in the range of, say, popular MOSFET will be plus minus 20 volts. So you can go, say, plus 15, minus 15, and this is just another way of doing it. And the question is, what's the benefit of using a bipolar, and when is it really needed? So there are a number of reasons for that, and I'm just going to refer to two or three of them, which are the important ones. First of all, we have the problem of so-called ground noise. Well, what is a ground noise? If we have say, a digital driver, this could be a controller, and then we have the driver itself, and then the MOSFET, the gate. And if we're not very careful in the layout, and then we have a common ground line or even a ground plane in which there is a current passing through, then obviously there'll be some voltage generated across this line because of the fact that whatever you do, it has some resistance and inductance. And these are not, this is not DC, these are pulses, and therefore you'll generate a voltage or potential difference between, say, this digital part and the driver, and the driver itself, and in this case, if this is a MOSFET, this will be the source. So we have this additional potential across this line. And therefore, even if the signal coming into the driver is clean, if it is entirely clean, then you'll see at the output of the driver a clean output, if this is a nice voltage. In this case it is not, but just assume that this is a sort of a perfect square wave pulses. You'll have at the output same pulses, only with capability of driving the gate, but the gate to source voltage will now be this plus this added noise, and consequently what the gate to source is seeing is something of this nature. This is just a noise here, or the potential difference between these 2 points. And if this is high enough, then it could actually reach the threshold of the transistor, and it will be conducting when it is not supposed to be conducting, which could be not only inconvenient, but actually harmful and lead to a disaster. So in this case, you can sort of improve the so-called immunity, noise immunity of the system by driving the gate bipolar. So in this case, even if I'll have some noise here, some EMI, which is superimposed on the gate signal, it will not reach, if it is negative enough, it will not reach the threshold. Of course, this voltage has to be high enough so the voltage or the noise superimposed on it will not go down to the threshold voltage level. So here we see that a bipolar can help to improve the noise immunity of the system by allowing a larger margin for the noise or for the disturbance. Now another reason, which is very important, I'll go over it briefly, is some voltages which are generated due to parasitic elements. So let's consider a half bridge. This transistor was conducting, therefore there is a current flowing this way, and now it is off and this transistor is conducting, and we are now at the dead time between the time that this transistor now is turned off until the upper transistor is turned on again. We needed the time in order to avoid, of course, a shoot through. So this transistor now is turned off, and consequently the diode will capture the current. This is now off, it's not conducting, so the current will be passing through here. And in this situation, the voltage that we're going to see here is the voltage drop on the diode. Here it is, it's a negative voltage. And the diode current is the current of the inductor. This is the diode current. Now, we are turning this transistor on. As we turn it on, starting to conduct, we are imposing a positive voltage here. And consequently, the current will start going down, the diode current going down. If it is a quick switch, then this would be like a resistance, RD is on, but due to the leakages in the line, the current is not building up quickly, but there is a certain slope depending on the voltage and the total stray inductance in the loop. So the current now is going down. As long as there is a current through the diode, the voltage across it is still about the same. So we see here still a lower voltage. And then we reach the point where the diode current is in fact almost zero, or crossing the zero. And here it is crossing the zero. This is the reverse recovery of the diode. I mean, this is the reverse current, and here is the reverse recovery. During this time, the current is actually in the opposite direction during this time. Okay? And then we have the recovery, and eventually, of course, the diode is not conducting, and all the current is actually passing through from the transistor to the output. Now, during this time of the reverse recovery, first of all, as long as there is a current in the diode, the voltage is approximately the same. As long as there is some charge carriers in the junction, doesn't matter whether it's one way or the other, so we have about the same voltage. And then once the reverse recovery is sort of finished, then we start seeing the voltage rise of this transistor due to the charging of the capacitor, and eventually it of course lock to the Vin. Let's have a look now at this situation in which we have a didt starting from a given point and then going down back to zero. There's a certain slope to it, a certain didt, and this didt is generating a voltage across this inductance. This is a stray inductance, could be part of it inside the package, the bonding between the die and the pin on the terminal, and some of it could be the traces out to this point. So we have a didt here, and there is a voltage building up in a direction that here it's plus and here it's minus. So consequently, although the voltage of the gate referred to ground is zero, we are now generating a positive VGS. This goes negative, this is zero, so there is a positive VGS. And if this voltage is high enough, the transistor will start conducting, which is very bad because we are going to have a shoot through. So this is one problem we have. We have this induced voltage due to the diode and the inductance that we have here. And in this case, going back to the bipolar drive, if this is not zero here, but rather negative, then we can allow more negative voltage across this inductor before we have any problem. It is important to realize that the IDT, which is of course important to the value of the voltage that you might get, the magnitude, it could be of different kinds, and there are some diodes which are with soft recovery, so that this IDT is slower, and consequently the voltages will be slower. So that was one problem, but then we have another problem. Once the voltage across this transistor starts to rise, we have now a dividity here, and this dividity here, at this point, is now causing a current to flow through this capacitor, CGD, the gate-to-drain capacitor. The current would be C dVdt. The higher, the faster dVdt, the higher will be the current. Now this current now will cause a spike here at the gate, because it's now injecting current here. There is a voltage divider, you might say. There is a capacitance here too. There is a resistor here. Obviously, the lower the impedance will be here, the lower will be the spike, but there is a limit to it. And this is why, by the way, you'd like to turn off very quickly. That is, this RG for the off direction is usually made smaller than the RG for the on direction. This is one reason for that. So due to this injection, we have this spike, which again could be high enough to turn this transistor on when it is not supposed to be, while the voltage on it is already high. So here is again a situation that by having the gate voltage going negative, if this would have been negative, then the spike, although existing, will not reach a dangerous value. So these are some of the reasons that you might wish to go to a negative voltage bipolar drive of the MOSFET. For IGBTs, this could be very important because IGBTs are large elements, inductances are relatively large, capacitance is large, and therefore it is customary for the IGBTs to have a bipolar drive. It is also correct for devices that have a narrow range permissible for the VGS. For example, a certain GaN transistor have only 0 to 6 volt range for driving. Above that, it could damage the device. So it can go negative too. So by going negative, you actually extend or improve the noise immunity of the element. And this is also similar to silicon carbide. Some of the units are also have a narrow range. So there is a need for this bipolar excitation. So now the question is, how can we get it? Now the obvious way would be to have a driver which has two power supplies, one plus, one minus, and you drive it with a regular 0 to whatever, say 15 volt, and then it generates a bipolar volt because this output can swing between VCC to minus or to VEE, and therefore you get this bipolar drive. So this is the simplest way, and there are some dedicated drivers for that. But you need a dual power supply. You can get by with a floating single power supply by dividing the voltage, not necessarily by half, but in some ratio, to generate two voltages. This point is now connected to ground, and then the supply therefore can swing between the plus and the minus. Again, it has to be a dedicated driver that has a ground as well as the VCC and VEE, that is that the ground is not the negative rail. Okay, so for this is a specialized driver that can accept a dual power supply. But there are ways to generate a bipolar signal from a unipolar signal, from just a positive pulse, and this would be by using a capacitor, which is sort of chopping off the DC. If you, for example, in this circuit, just a demo circuit, if you have a sort of PWM type of a signal coming in, there is a capacitor. This capacitor does not pass the DC, it's blocking the DC, and therefore the signal that you'll see here will be bipolar in such a way that the area here, of course, is equal to the area here. It's an AC signal. But as shown, this will be very sensitive to the duty cycle, because if the duty cycle is, say, very small, then you'll have a high pulse, and then here it'll be lower negative value, okay, because the areas are to be the same. And this will be also correct if you have here a capacitor which is smaller than this one, and so basically you'll have the same type of a behavior here too. And this capacitor now I am actually describing by this a typical gate input to a MOSFET. You have a total capacitance. I'm talking about the total capacitance that you have to charge. And again, if this total capacitor is smaller than this, or let's put it this way, you choose C1 to be a larger, significantly larger than here, then you get the same behavior. But as I've said, this is just not good enough. So what can be done to make it better? Well, there are a number of ways. Here's method, call it A. You start with a pulse like this. You have a capacitor, but then you have a Zener across it. So the capacitor will be charged only to the value of Vz. The rest of it will get to the gate. So the gate will get the drive voltage minus Vz. This is the gate voltage, the positive part. Now when this voltage here goes to ground, we see here actually the voltage across the capacitor, but with a minus sign. So we're going to see here Vz. So this arrangement now makes a positive voltage, positive pulse of Vd minus Vz, and a negative one, which is the negative voltage, which is very nice. Another way, which is kind of symmetrical, we might say, or complementary, is to put a Zener here. In this case, you clamp the voltage here to Vz, so obviously the voltage of the gate will be no more than Vz, and then you charge, though, the C1 to the difference between Vd and Vz, so here will be a negative value of Vd minus Vz. So this is another way to go, and to get this bipolar pulses. A third way would be to put two Zeners back to back, such that the positive will be one value, this value plus the voltage drop on the diode here, and then on the negative part you'll see the negative Zener as a voltage to the gate. So in this case you sort of clamp the gate to the two voltages. The rest will be the voltage of C1. And then depending on the value of Vd, you may have either, if Vd is exactly the sum of these two, then this capacitor will have a constant voltage. But if VD, say, is larger than the sum of two, then you'll have some charging and discharging, as I'm showing here. But the end result here is, again, that during the positive part of the pulse, we see here VZ, 1, this one, and during the negative part, we're going to see here VZ2, which is clamped again by this Zener. So this is another way to go. You can find in datasheet and application note examples of such a drive, a bipolar drive. This is, for example, from an analog devices application note. We have here a isolated driver. This side needs a power supply. We have here now two power supplies. One is positive and well, negative toward this rail. This is the original ground. Now it's negative voltage, refer to this point. This is now the source. So the swing now is between here and here, so it is positive and negative, and by this you get a bipolar drive to the transistor. This is floating entirely. There is no connection, of course, between this ground and this ground, so this part is getting its signal through an isolation, and then you have these two rails, positive and negative. The swing is between them, and the ground is connected, in this case, to the minus, okay? And so the whole thing is sort of floating. You need then a, in this case, it is shown as a dual supply. Another way to go would be to use a single supply. This is a floating supply, but then to use a Zener in order to get one part. This would be the negative part, and then the rest of it is the positive part. This is now connected to the source, so the swing is between the voltage here and the voltage here. So whatever, if this is a 5 volt Zener and this is a 25 volts, so you're going to have a 20 volt swing to the positive and minus 5 volt to the negative. That's a bit too high, but that's what it is here. Here we see a drive which has a larger resistor for turning on and a smaller resistor for turning off, as I've mentioned earlier. So this is a possibility for a driver that will be supplied by sort of a split source. And here is the example that I've shown earlier. This is the Zener across this coupling capacitor, and we have seen this before. And here the only difference is we see here the on resistor, the off resistor. This is just a bleeding resistor, so because you have a capacitor here, the gate is capacitance, so you need some sort of a leeway for, say, leakages, leakage current, etc. So this is just a bleeding resistor, and here it's shown for the upper and lower transistor the same thing. There is a paper that describes some of these approaches, and I've just brought one paper here, and here they're showing, similar to what we've seen, there is a Zener across the capacitor. There is another Zener, however, across here. Well, this Zener should be considered as a protection, because obviously you don't want a situation in which the voltage of this driver is higher than the sum of these Zener voltages, because if it is, then there'll be a current during the plus, and this could be a heavy current. You don't want this. So this is like, let's consider it as a protection in case there is some over voltage for some reason or another, and so basically this is actually doing the job. This is not. And finally, I'm showing this other approach that I've shown earlier, and this is by GaN systems. And this is for a GaN transistor, gallium nitride transistor, in which the drive is supposed to be, in this case, I believe, +9, -5 or -6. And here we have the back-to-back Zeners, and this is the coupling capacitor, and again we have the two resistors for turning on and turning off, and we see here the two drivers for the lower and upper side of a half bridge. Finally, I'd like to show a solution which is kind of an old one, but it's kind of interesting. This is from a datasheet by International Rectifier, which was bought by Infineon, so now it's Infineon. And basically what it is this is a driver. So there's nothing special about it. I'm not going to go over it. But the nice thing here is that they are generating the negative voltage, which is the negative rail for this driver. This driver is now between +15 and a negative voltage. It turned out to be -12 because it's not exactly 15. And then the driver is between these two. I mean, the output pulse is between the +15 and -12. Now, the nice thing here is that the minus voltage, this one, is generated by the pulses themselves. Okay, there is no auxiliary power supply, and there is a constant negative voltage, which is generated again by the pulses, by the PWM pulses. Now, this is done by a switched capacitor converter, you might say, which is inverting. It's a 1-to-1, and the way it works is the following: when the voltage is plus here, it's high, then this capacitor is charging to ground. This is the return, this is the ground of the input. And then as the voltage goes down, so there is a short between this and this, then we see that the voltage is, the plus is grounded, and the negative now is connected to this rail here through this reverse diode. So therefore this capacitor is now charged to this voltage of this capacitor in the polarity shown here. So the pulses, the PWM pulses themselves, are generating the minus rail here, the minus power supply needed for this bipolar driver. It's neat, and that's just another way to go. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.